Bonding is essential for metal piping systems and grounded metal parts that come into contact with circulating water. These components should be bonded together using a copper bonding jumper. The bonding jumper can be insulated, covered, or bare, but it must be no smaller than 8 AWG solid. The primary purpose of bonding is to ensure that all metal components are at the same electrical potential. This prevents the buildup of static electricity or stray currents, which can pose significant risks. Proper bonding also helps to protect against electrical shock and damage to equipment. The bonding jumper should be connected to the grounding system of the facility to effectively equalize the electrical potential. Bonding should be performed using approved methods. These methods include mechanical clamping, welding, or soldering. Each of these techniques provides a reliable electrical connection. Mechanical clamping involves using a clamp to securely fasten the bonding jumper to the metal components. Welding involves fusing the bonding jumper to the metal components using heat and a filler material. Soldering involves joining the bonding jumper to the metal components using a solder alloy and heat. It is critical that bonding connections are inspected and maintained regularly to ensure proper conductivity. Over time, connections can loosen or corrode, which can reduce their effectiveness. Regular inspections can identify potential problems before they lead to electrical hazards or equipment damage. In areas where the circulating water is corrosive, special precautions may be necessary to protect the bonding jumper from damage. Corrosion can degrade the bonding jumper and reduce its conductivity. Protective coatings or corrosion-resistant materials can be used to mitigate the effects of corrosion. Proper bonding is crucial for the safe and reliable operation of any system that involves circulating water or metal components. Firstly, it prevents electrical hazards by ensuring that all metal parts are at the same electrical potential. This eliminates the risk of electrical shock and reduces the likelihood of equipment damage caused by stray currents. Secondly, it protects equipment from damage by preventing the buildup of static electricity or stray currents. These currents can damage sensitive electronic components and reduce the lifespan of equipment. Thirdly, it minimizes the potential for injury to personnel by reducing the risk of electrical shock. Electrical shock can cause serious injury or even death. By ensuring that all metal parts are properly bonded, the risk of electrical shock is significantly reduced. To summarize, bonding is an essential safety measure that should be implemented in any system that involves circulating water and metal components. Here is some additional information to consider. Firstly, the size of the bonding jumper is critical. An 8 AWG solid copper conductor is generally the minimum size required for bonding metal piping systems and grounded metal parts. However, the specific size may vary depending on the application and local electrical codes. It is essential to consult with a qualified electrician to determine the appropriate size for the bonding jumper. Secondly, the type of bonding jumper is also important. Insulated, covered, or bare copper conductors can be used for bonding. Insulated conductors provide additional protection against electrical shock. Covered conductors provide protection against physical damage. Bare conductors are typically used in areas where there is no risk of physical damage or electrical shock. Thirdly, the location of the bonding jumper is also a consideration. The bonding jumper should be connected to the metal components as close as possible to the point where they come into contact with the circulating water. This minimizes the impedance of the bonding path and ensures that all metal parts are at the same electrical potential. Fourthly, the method of connection is also important. Mechanical clamping, welding, or soldering can be used to connect the bonding jumper to the metal components. Each of these methods provides a reliable electrical connection. However, the specific method used should be appropriate for the application and the materials being joined. Fifthly, the inspection and maintenance of bonding connections is also critical. Bonding connections should be inspected regularly to ensure that they are tight and free from corrosion. If any problems are found, they should be corrected immediately. In corrosive environments, it may be necessary to use special precautions to protect the bonding jumper from damage. Protective coatings or corrosion-resistant materials can be used to mitigate the effects of corrosion. Sixthly, it is important to consult with a qualified electrician to ensure that all bonding requirements are met. A qualified electrician can assess the specific application and determine the appropriate bonding methods and materials. They can also perform the bonding work and inspect the connections to ensure that they are properly installed. Here are some examples of systems that require bonding. Firstly, plumbing systems. Metal water pipes, gas pipes, and drain pipes should be bonded together to prevent electrical hazards. Secondly, HVAC systems. Metal ductwork, chillers, and pumps should be bonded together to prevent electrical hazards. Thirdly, swimming pools. Metal pool structures, pumps, and filters should be bonded together to prevent electrical hazards. Fourthly, industrial equipment. Metal machinery, tanks, and piping should be bonded together to prevent electrical hazards. Fifthly, electrical systems. Metal conduits, enclosures, and grounding electrodes should be bonded together to ensure a low impedance ground path. Here are some common mistakes to avoid when bonding metal piping systems. Firstly, using an undersized bonding jumper. An undersized bonding jumper may not be able to carry the fault current, which can lead to electrical hazards. Secondly, using an inappropriate bonding method. Using an inappropriate bonding method can result in a poor electrical connection, which can increase the risk of electrical shock. Thirdly, neglecting to inspect and maintain bonding connections. Neglecting to inspect and maintain bonding connections can allow corrosion to develop, which can reduce the effectiveness of the bonding system. Fourthly, failing to consult with a qualified electrician. Failing to consult with a qualified electrician can result in improper bonding, which can increase the risk of electrical hazards. In summary, bonding is an essential safety measure that should be implemented in any system that involves circulating water and metal components. By following these guidelines, you can ensure that your system is properly bonded and that you are protected from electrical hazards. Bonding is a critical aspect of electrical safety, particularly in systems involving metal piping and circulating water. It's a practice designed to equalize electrical potential across all metal components, mitigating the risk of electrical shock and preventing damage to equipment. The following points elaborate on the key considerations for effective bonding. Firstly, the selection of the appropriate bonding conductor is paramount. An 8 AWG solid copper conductor is generally considered the minimum acceptable size. However, the specific requirements can vary based on local electrical codes and the specific application. Factors such as the potential fault current and the length of the conductor influence the sizing decision. Consulting a qualified electrician is crucial to ensure compliance and safety. Secondly, the type of conductor is also a significant factor. Copper is the preferred material due to its excellent conductivity and resistance to corrosion. The conductor can be bare, covered, or insulated. Insulated conductors offer enhanced protection against accidental contact, while covered conductors provide a degree of physical protection. The choice depends on the environment and the specific risks involved. Thirdly, the method of connection must ensure a reliable and low-resistance electrical path. Approved methods include mechanical clamping, welding, and soldering. Each technique has its advantages and disadvantages, and the selection depends on the materials being joined and the specific application requirements. Mechanical connections should be tight and corrosion-resistant. Welding provides a permanent and robust connection, but may not be suitable for all materials. Soldering is a common method for smaller conductors but requires careful surface preparation. Fourthly, the location of the bonding connection is critical. The connection should be made as close as possible to the point where the metal components come into contact with the circulating water. This minimizes the impedance of the bonding path and ensures that all components are effectively grounded. Multiple bonding points may be necessary for larger or more complex systems. Fifthly, regular inspection and maintenance are essential to ensure the long-term effectiveness of the bonding system. Connections can loosen over time due to vibration or thermal cycling. Corrosion can also degrade the connections, increasing resistance and reducing their ability to carry fault current. Regular inspections should include visual checks for corrosion, loose connections, and physical damage. Electrical testing can also be performed to verify the continuity and persistence of the bonding path. Sixthly, corrosion protection is a crucial consideration in environments where the circulating water is corrosive. Corrosion can rapidly degrade the bonding conductors and connections, compromising the effectiveness of the system. Protective coatings, such as epoxy or paint, can be applied to the conductors and connections to prevent corrosion. Alternatively, corrosion-resistant materials, such as stainless steel or copper alloys, can be used. Seventhly, bonding should be integrated with the overall grounding system of the facility. The bonding conductors should be connected to the main grounding electrode system, ensuring a low impedance path to ground for fault currents. This helps to protect against electrical shock and minimize the risk of equipment damage. Eighthly, compliance with local electrical codes is mandatory. The electrical codes provide detailed requirements for bonding and grounding, including conductor sizing, connection methods, and inspection procedures. It is essential to consult the relevant codes and standards to ensure compliance and safety. Ninthly, documentation is an important aspect of bonding. A record of the bonding system should be maintained, including the location of bonding connections, the type of conductors used, and the results of inspections and tests. This documentation can be valuable for troubleshooting and maintenance purposes. Tenthly, professional expertise is essential. Bonding and grounding are complex topics that require specialized knowledge and skills. A qualified electrician should be consulted to design, install, and maintain bonding systems. This ensures that the system is properly installed, compliant with codes, and effective in protecting against electrical hazards. Here are some specific examples of systems that benefit from proper bonding. Firstly, plumbing systems, including water pipes, gas pipes, and drain pipes, should be bonded to prevent electrical hazards. Secondly, HVAC systems, including ductwork, chillers, and pumps, should be bonded to protect against electrical shock and equipment damage. Thirdly, swimming pools, including pool structures, pumps, and filters, require bonding to ensure the safety of swimmers. Fourthly, industrial equipment, including machinery, tanks, and piping, should be bonded to protect workers and prevent equipment damage. Fifthly, electrical systems, including conduits, enclosures, and grounding electrodes, must be bonded to create a low impedance ground path. By adhering to these principles and best practices, you can ensure that your metal piping systems and equipment are properly bonded, providing a safe and reliable electrical environment. The NEC, or National Electrical Code, provides guidelines on how to achieve proper bonding. The NEC provides the minimum standards for electrical safety, and its recommendations should be followed diligently. For example, NEC Section 250.92 discusses bonding service equipment. It states that the grounded conductor must be bonded to the service equipment enclosure and the grounding electrode conductor. This ensures that all metallic parts are at the same potential, reducing the risk of shock. NEC Section 250.104 covers bonding of metal water piping. It requires that metal water piping systems be bonded to the service equipment enclosure, the grounded conductor at the service, the grounding electrode conductor, or the grounding electrodes. This is crucial because water pipes can become energized if they come into contact with electrical wiring. NEC Section 250.118 lists the types of equipment grounding conductors that are acceptable for bonding. These include copper, aluminum, or copper-clad aluminum conductors. The conductor must be sized appropriately for the overcurrent protection device in the circuit. NEC Table 250.122 provides guidance on the minimum size of equipment grounding conductors based on the rating of the overcurrent protection device. For example, for a 20 amp circuit, the minimum size is 12 AWG copper or 10 AWG aluminum. NEC Section 310.16 provides ampacity ratings for conductors. It is important to select a conductor size that is capable of carrying the expected current without overheating. NEC Article 430 covers the grounding and bonding of motors. It requires that motor frames be grounded to prevent electrical shock. NEC Section 430.145 provides guidance on the size of the equipment grounding conductor for motors. NEC Article 500 covers hazardous locations. It provides additional requirements for bonding and grounding in areas where flammable materials are present. NEC Section 501.30 requires that all metal raceways, enclosures, and equipment be bonded together in hazardous locations. NEC Section 547.9 covers agricultural buildings. It provides specific requirements for grounding and bonding in agricultural buildings to protect livestock from stray voltage. NEC Article 680 covers swimming pools, fountains, and similar installations. It provides detailed requirements for bonding all metal parts of the pool structure and equipment to prevent electrical shock hazards. NEC Section 680.26 provides specific requirements for bonding the perimeter of the pool with a solid copper conductor. The conductor must be at least 8 AWG and must be connected to all metal parts of the pool structure and equipment. NEC Section 690.43 covers solar photovoltaic systems. It requires that all exposed metal parts of the solar array be grounded and bonded to prevent electrical shock. NEC Section 700.9 covers emergency systems. It requires that emergency systems have a reliable ground to ensure proper operation during a power outage. NEC Section 701.7 covers legally required standby systems. It provides requirements for bonding and grounding these systems to ensure their reliability. NEC Section 702.7 covers optional standby systems. While not legally required, proper bonding and grounding are still recommended for these systems to ensure safety and reliability. It is crucial to remember that the NEC is a comprehensive document, and it is important to consult the specific sections that apply to your particular situation. Engaging a qualified electrician is essential to ensure that your electrical system is properly bonded and grounded, and that it complies with all applicable codes and standards. Ignoring these guidelines can lead to significant safety hazards, including electrical shock, equipment damage, and even fire. Therefore, prioritize safety and always adhere to the NEC requirements for bonding and grounding. Remember that electrical codes can change, so it's a good idea to consult the latest version of the NEC.